Every single second of your life, you're literally surrounded by an invisible world that's constantly in motion. It's in the light you see, it's in the sounds you hear, it's even in the phone that's probably in your pocket right now. So today, we're going to make that invisible world visible. We're diving into the fundamental properties of waves.
So let me ask you this. What in the world connects the sunlight warming your face, the ripples spreading across a pond, and the sound of your favorite song? I mean, they seem like completely different things, right? But they all share a secret identity. Yep, they are all waves. And by the end of this, you're going to understand exactly what that means.
So to get to the bottom of that question, we've got to start with the most basic piece of the puzzle. What exactly is a wave? At its heart, it's really all about energy on the move.
Okay, here's the core idea, the most important thing to get. A wave is just a disturbance that transfers energy from one place to another. And the key word there is energy. Waves move energy, they do not move matter. It's kind of like a rumor spreading through a crowd. The story moves all the way across the room, but the people themselves pretty much stay put. This is the perfect way to picture it. Imagine a duck just chilling on a lake. When a wave comes along and passes under it, what happens? The duck just bobs up and then back down. It doesn't get carried all the way to the shore with the wave. And that's because the wave is moving energy through the water, but it isn't actually carrying the water, or the duck, along with it. All right, so we've established that waves move energy, but how do they do it? Do they all travel in the same way? Not a chance. And the first big difference between them all comes down to one simple question. Do they need something to travel through?
And that something has a name, a medium. A medium can be a solid, a liquid, or a gas. Anything from the ground under your feet to the air you're breathing right now. For a whole class of waves, this medium is basically their highway. Without it, their energy has absolutely nowhere to go. So these waves that absolutely must have a medium are called mechanical waves. And the name kind of gives it away. They need a physical, mechanical substance to travel through. A sound wave needs air particles to vibrate against each other. An earthquake needs the ground to shake. No medium, no wave. It's a whole reason why in space no one can hear you scream. There's no air for the sound to travel through. And yeah, sound and water waves are the two classic examples of mechanical waves. Sound absolutely needs that medium of air to get to our ears, and those ripples need the water to spread out across the pond. They both have to have that highway to get their energy from point A to point B.
Okay, but this brings up a really fascinating problem, doesn't it? If some waves need a medium, how on earth does light from the sun, which is millions and millions of miles away, travel through the vast, empty vacuum of space to reach us here on Earth?
Well, the answer lies in our second major type of wave, the electromagnetic wave. These guys are the rebels of the wave world. They don't need a highway, they just build the road as they go. They can travel through the absolute nothingness of a vacuum, no problem at all. Light is, of course, the most famous example, just zipping through the void of space to bring us sunlight. But this category is huge. It also includes the radio waves that carry our music, the microwaves that cook our food, and even the X-rays that let doctors see inside our bodies. They are the great cosmic travelers of the universe, and our modern world would not exist without them. So here it is, the first big dividing line. On one side, you've got mechanical waves. They're a bit needy. They require a medium to travel. And on the other side, you have the electromagnetic waves, which are totally self-sufficient. This is the first fundamental way to classify any wave you come across. But whether or not a wave needs a medium isn't the only way to sort them. There's another way, and this one is all about how the actual particles within that medium move. You could think of it as the choreography of the wave's dance. First up, we've got the transverse wave. Now, this is probably the shape you imagine when you hear the word wave. The energy travels forward, but the particles of the medium itself move up and down at a right angle or perpendicular to the direction the energy is going. It creates that classic wavy shape we all used to doodle in our notebooks. The other type of dance is the longitudinal wave. The best way to picture this one is to think about pushing a slinky. The little pulse of compression moves forward, but the individual coils just move back and forth along the exact same line. The particle motion is parallel to the direction of the energy. So, we've got two different ways to classify waves, by whether they need a medium and by their dance moves. Now, let's get a little more specific and actually learn the language we use to talk about the different parts of a wave. Let's look at its anatomy. For a transverse wave, the language is super intuitive. The highest point, the very peak, is called the crest. And the lowest point is called the trough. You got your peaks and your valleys. Simple as that. And now we can start measuring them. Amplitude is the wave's height from its middle resting position. And this is so important because amplitude tells us about the wave's energy. A taller wave has more energy. Just think about a tiny little ripple in a pond versus a giant tsunami. And then there's wavelength, which is the distance from one crest to the very next one. This measurement determines things like the color of light or the pitch of a sound. Now, longitudinal waves don't have crests and troughs. Remember, they look different. Instead, they have these squished up parts and these stretched out parts. The areas where the particles are all packed tightly together are called compressions. And the areas where they're really spread apart, those are called rarefactions. It's that pulse of compression that moves through the medium. All right, we have covered a lot of ground. So now, let's put all of these new concepts to the test. We're going to use our new vocabulary to do a head-to-head comparison of two of the most important waves in our lives, sound and light. This diagram just lays it all out perfectly. Okay, let's look at sound. It's a longitudinal mechanical wave. What does that mean? It means it's a compression wave, and it needs a medium, which again is why it can't travel in space. Now look at light. It is the exact opposite. It's a transverse electromagnetic wave. That means it has that classic up and down shape, and it's perfectly happy traveling through the vacuum of space. But what's that in the middle? What do they share? The one thing that makes them both waves. They both transport energy. So, what are the big takeaways here? First, the golden rule. You have to remember this. Waves move energy, not stuff. Second, every wave you'll ever encounter fits into two boxes. Is it mechanical and needs a medium, or is it electromagnetic and can travel freely? And third, what's its dance move? Is it transverse, going up and down, or is it longitudinal, pushing back and forth? With just those few ideas, you can describe pretty much any wave in the entire universe. So I'll just leave you with this thought. Now that you understand the hidden language of waves, the compressions in a sound, the wavelength of light, which everyday thing are you going to see completely differently now? The next time you see a rainbow or maybe hear an echo, you'll actually know the secret dance of energy that made it all happen. Thanks for watching.